This dataset has been designed so that the signal to noise in each image is relatively low. And this has consequences when we perform principal component analysis. One of which is that when we reconstruct spectra at the pixels based on 3 abstract factors, we see negative going peaks. This is non-physical and is an indication that the calculation is only an approximation to what the spectra pixels actually are. We can see it in the negative going peaks. Perhaps we can't see it so well in the positive going peaks. But the point is that the calculation performed on data of this form does have limitations. I can simulate what would happen if I'd spent more time collecting these data. And I can do that by using a mechanism by which pixels are summed to produce more intensity but less pixels. And this is done on the image processing dialog window, the image processing property page, using the change size button. So all the images overlaid in the active tile, I use the reduce image option and press OK. I end up with a new data set. And the new data set now has a set of images with a quarter of the number of pixels and 4 times the intensity. So we could do this again. Overlay all the images in the active tile, and then we end up with a further reduction in the size of the image, and we have a further increase in the signal in each pixel. So let's do this one more time. And now we have a set of images which, when converted to spectra at pixels, actually have spectra that have information that would allow us to perform a principal component analysis, and the influence of these negative going peaks will be reduced as a consequence of the improved signal to noise. We can perform the PCA calculation on the spectra, and if we do that using optimum scaling, we end up with a set of images, and these images give us an indication of the number of abstract factors. What's interesting is that we start to get something that looks like a feature down the middle here. So instead of purely having 3 abstract factors, it looks like there may be 4. Let's close the images and just look at the spectra. So without doubt we are producing similar abstract factors in terms of abstract spectra, and well, there's the 4th one. It looks like we're seeing a little bit more variation that is being pulled out of the data set as a result of having the reduced number of spectra with better signal to noise. But essentially we still have the 3 abstract factors that we had before that were representative of gold and silver and mostly the glass. But it's not really mostly the glass. What it is the total spectrum. It's not quite the total spectrum. PCA doesn't calculate the total spectrum, but it's very close to it. We have to iterate to get to this spectrum. You don't have to iterate to calculate the average spectrum. But the essential features are the same. You've got a little bit of gold. That's because there's a thin gold wire. You've got some silver. That's because up in the top right hand corner there was silver. And then the rest of the image was glass, so you see a lot of silicon, carbon and oxygen. So these all have the same characteristics, but if these are then returned to the original state and we calculate, in this case let's still use 3 abstract factors, so I'm omitting some of the information that I think is now present in the 4th abstract factor, and we produce a set of spectra, and I can look at these if I use an option on the VAMAS info page where I can convert from corresponding variables to VAMAS blocks, and that lets me have a look at the spectra and inspect where I see the problem. So this is where I'm expecting to see negative going peaks, and there's some evidence of a little negative going peak somewhere there, but it's nowhere near the problem that we saw before. And that's because the PCA reproduction step is effectively forming a linearly square solution based on the abstract factors. And since the abstract factors are now guided more by signal and less by noise, we stand a better chance of getting a good reproduction of the data, because we now have better signal to noise, the same abstract factors, and the least squares solution is more capable of reproducing the spectroscopic shapes.